Am I online? Can you hear me? Yes?
Yes, Professor.
Good, okay. So, where were we? Let me go full screen. So we have a pointer. So we've seen quite a bit already about how to handle the crystal Hamiltonian, the various approximations that we had to make in order to proceed to render the problem tractable. Today we're going to see a little bit why the last things that we saw, which is the obvious idea, plugging into the single electron effective Schrödinger-like wave function that we found for the crystal, for the electronic part, plugging in the block expression for the wave functions. Let's see why it doesn't work. I mean, I mentioned it already. We end up with a matrix, we review it briefly, and this matrix is just too large. And so this will lead us to the concept of pseudopotentials, which is what we're going to deal with at first today. And I'll give you then a computational example, how to calculate using empirical pseudopotentials that will make the difference, the distinction between self-consistent and empirical pseudopotentials. I'll give you a simple example of how to calculate the band structure of some semiconductors of interest for us. Having done that, we'll move to different methods that are not based on plane wave expansions, which is what this pseudopotential essentially is based on. And actually we'll show how Walter Harrison derived the concept of pseudopotential starting from orthogonalizing the plane waves. So we'll see other methods which are based on a different choice of basis functions for our wave function. Mainly the tight binding, which is an expansion of on atomic orbitals, and then a very commonly used approximation perturbation theory, which is the K.P method. We'll review briefly what DFT does. So having done this review, then I'm not sure whether we'll get to it completely today, but hopefully in the second part of this lecture, we'll talk about the single electron dynamics. This is quite important for us, particularly dealing with transport. The idea behind this topic that we will discuss is, having seen the complicated nature of the electronic excitation spectrum of a crystal at zero temperature, in absence of any external perturbation and so on, what do we do when we apply an external bias, an external perturbation? How do we treat the electronic motion in this messy situation? And the idea is that there are very powerful theorems, well, the two acceleration theorems, and a way to approximate the single electron wave function in a present of an external potential. It has different names, we'll go into details, that simplify our lives, and we'll be able to deal with transport in a kind of unexpectedly simple way. Probably next week, I posted already some slides about how to go about calculating the band structure, so the electronic excitation spectrum of a nanosystem. All of this stuff that we have seen so far, and we will see later on today, deals with bulk crystals. Nowadays, there's a lot of interest, of course, in low dimensionality structures, but even in the past couple of decades, there's been a lot of interest, for example, in thin body silicon on insulator transistors. Nowadays, the transistors that you can buy are mainly FinFETs, which are tiny objects, not as tiny as we will deal with here, but tiny enough. So how do you do about calculating the band structure in a system which is not periodic as a crystal, a bulk crystal is? Clearly, if I consider a nanowire, for example, I'm losing periodicity in 2 dimensions. I retain the periodicity along the axial direction of the wire, I lose it in the other 2 directions. So how do I go about using plane wave methods to calculate the band structure of such a system. These slides, I've posted them, I'll keep tweaking them. I also I want to inform you that I have posted, I don't know if you've seen it, some what we call here homework problems, problem sets. They are just sets of problems that you may want to work on. I've posted the problem, file with the problems, and the file with the solutions. It's just for you to make sure that you're in sync with what we are dealing with. Don't look at the solutions without at least having tried to solve the problems yourselves. Okay, so let's move on. We have to introduce the concept of pseudopotentials, which is something that goes back to, I think, 1960s. Maybe there were some ideas even a little earlier. Actually, there are two different, how could I say, concepts behind what we mean by pseudopotentials. Sometimes they're kind of confused. One is, let's call it the rigorous way, which is to start from the orthogonalized plane waves, which is a concept that I introduced last time, and consider what is the single electron Schrödinger equation. It's a Schrödinger-like equation. I'll call it Schrödinger, but I think I've already put a lot of caveats on how to interpret the eigenvalues, for example, using Koopman theorem. So what is the wave function that the projected wave function, the wave equation that the projected wave function has to obey, projecting out the core states that we're not interested in? Another way, which is sort of, they sort of merge together, although historically they started from different sides, is the concept of model potential. Essentially, it's an empirical way to model the potential of the ions, accounting for all of these complicated elements, exchange and correlation mainly, but also the Hartree potential in the case of an empirical model that we saw enter our problem. So let me remind you what we were doing last time. We looked at the single electron Schrödinger-like equation. This is the kinetic energy of an electron, the wave function here. We already know what it means, I hope. It's just coming from the fact that we have expressed the full wave function of many electrons, already keeping the ions fixed at their equilibrium position. We have looked at the wave function expressed in terms of a Slater determinant in order to respect the fact that the full wave function has to be antisymmetric with exchange of the indices of two electrons. All of these manipulation at the end will come out with an equation which looks very much like Schrödinger equation for a free electron in the presence of a rather complicated and messy potential, which is the periodic ionic potential. And here I've lumped all of the nightmare issues that we've dealt with, exchange, correlation, the Hartree potential, and whatnot. Anyway, it's something that is periodic. We know that we can use the block form for the wave function. So we simply plug this expression from Bloch's theorem into the single electron Schrödinger equation. We did some manipulations, essentially having plugged in, then we projected into a state with a different G prime over here, and we ended up with a semi-infinite matrix. This is a matrix. These are the diagonal terms of the matrix. If you want to bring this on the other side, this is an eigenvalue problem. So we have a matrix which is the kinetic energy on the diagonal, and then we have some off-diagonal terms. Eventually, when the kinetic energy is big enough, when G is sufficiently large, remember this is just the kinetic energy of an electron, so we're considering an electron at very high kinetic energy. Hopefully, the ionic potential gets weaker and weaker. So at some point we have to deal with a matrix that for large G's is diagonally dominated. So we can decouple it from the upper portion of the matrix. And so we can truncate it up to sufficiently large G, where these numbers are sufficiently small compared to the diagonal term. And then we solve our eigenvalue problem. And of course, the eigenvalues having fixed a particular wave vector inside the Wigner-side cell in reciprocal space, which is called the Brillouin zone. So we consider a K inside the Brillouin zone. For each K, we get a different bunch of eigenvalues and eigenvectors. This is the secular equation that determines the eigenvalues E of K, which is the band structure. If we move K all of these eigenvalues, each of them corresponding to a particular band, moves along and gives us the dispersion of the electrons. And we saw that we can simplify the potential using the fact that this is a periodic expression. This is expressed explicitly in terms of the position of the ions, the singularities of this potential. We saw that we can manipulate it in a particular way we discussed last time by exploiting explicitly the periodicity that we have, looking at the properties of the G vectors. At the end, I just summarized what we found last time. For a case of, say, silicon or diamond or germanium, so a monoatomic, monoelemental solid crystal, the Fourier transform of the ionic potential, ionic plus the rest, exchange, correlation, hierarchy, and so on, essentially is the product of two factors. One is what is called the structure factor that depends on the geometry. It is this sum, where tau sub alpha are the positions of the ions in a single primitive cell. And this instead is the form factor, which tells us something about the strength of the ionic interaction. So this is all very nice. The problem is that, as I told you, we have to truncate this matrix at some point for some G. So we have to look at how far do we have to go with these G vectors in order to be able to ignore the ionic potential. And the problem is that if I take the bare ionic potential, its Fourier transforms actually goes down like 1 over q squared. This is the q component, Fourier component. This is not fast enough. And the problem is the singularity. Near the ion core, the potential changes very fast. It goes actually to minus infinity. It's an attractive potential. So the problem is that if I do a little bit of a back of the envelope calculation, how many G vectors I need for silicon, I end up with way too many, the order of 1,000,000. Again, here we are back in time to the 1960s. Now probably solving an eigenvalue problem of rank 1,000,000 would not be considered to be impossible. Laborious, we would have to do some effort, but probably solvable, particularly if it is a matrix which is diagonally dominated. But in those days, it was impossible. So the question is, we cannot just use brute force to calculate the band structure of our crystals, because the rank of the matrix whose eigenvalues and eigenvectors we have to find is just too large. The question is, do we really need this information which is actually causing troubles? Do we really need information about what happens near the core, the ionic core? After all, the ionic cores, as I told you already a few times previously, they're very deep. Again, in case of silicon, for example, the 2p states are some 120 eV down. If we're interested in a band structure which has a band gap of 1 volt or so, and we're interested in a few EVs around the band gap, do we really need to worry about these states that do not participate or contribute to the bonding, so they don't affect the crystal structure? So the idea, as I told you, was the idea that Harrison had. Again, I haven't corrected this. It was Harrison who said, well, we know that this is an eigenvalue problem with a Hermitian over here, a Hermitian matrix. The eigenvectors will be corresponding to different eigenvalues will be orthogonal. The core states, therefore, have to be orthogonal to the valence states, the bonding states that we want to consider. So why don't I consider the wave function, the real wave function, but I subtract out its projection over the core states, which are orthogonal. So this is what is called the orthogonalized plane wave. So I start for the block function. I use this ket notation for the block function, but I subtract out this object. This is the projector over the subspace spanned by the core states of each ion. So instead of considering my plane wave with full periodic components, the U function of the Bloch theorem, that is, as I told you, the remnant of the orbitals and also the core states, I take out the core states. Those are exactly those that oscillate fast, very fast near the core and give me all the problems. So what I'm going to consider is just this orthogonalized plane wave. And I'll push the analogy forward a little further in the next couple of slides, saying how this, using this idea, I can find what is the wave function that this orthogonalized plane wave has to obey once I remove the core states. And it will be a wave function will be very similar to the one that we have considered so far, except that the lattice potential now becomes a different object. And this different object is the pseudo potential. So let me just sketch again. This is a sketch that I had last time. The green lines are the ionic potential in this ideal cartoon-like one-dimensional crystal. And the problems are coming from the cores, from the fact that here the potential changes very fast, and this gives me that slow decay 1 over q squared or 1 over g squared of the Fourier components of my potential. Why don't I chop it off? Now here is kind of brutally chopped. I have here a better picture of what's going on. So consider one ion. This is the singularity. It's the position of the, the position, where am I? Here, the position of the ion. This is the potential, the bare ionic potential. Of course, I will have to add to this potential the screening effects so the Hartree potential of the other electrons. I would have to add the exchange and correlation effects. Let's ignore that for now. The problem is coming from the fact that this goes to the singularity. So it has very high frequencies, spatial frequencies in my Fourier components. Now, I'm not really interested in what happens here. Here is a radius, let's call it a cutoff radius, beyond which the core states don't contribute anymore. And outside this sphere that surrounds each ion, that's where the bonds are. That's for silicon, my sp3 orbitals constitute the bonds of the crystal, of the solid. So what happens inside, in principle, I have some wave function which has some nodes. It oscillates fast. Again, this is the cause of my problem. So the fact that I have very large G vectors that I have to use in order to capture these variations. But really, I don't care about what happens here. These are the core states. Why don't I replace the potential with something smooth which avoids the singularity? It goes to some value. We'll talk a little bit about how to approximate it better. And the wave function, therefore, will not oscillate anymore. So, and this will result in getting rid of all of the high frequency components, spatial frequency components of the potential that I dislike, that render my life uneasy. The idea is that if I can find a way to match the wave function and its radial derivative at the core, at the boundary between the core and the bonding region, since a Schrödinger equation, or the Schrödinger-like equation that I'm dealing with, is the second order differential equation, partial differential equation, if I match the boundary conditions here to the correct boundary condition, then I'm guaranteed to have the correct solution outside the core. And this object, this fake potential, that, however, is guaranteed, if I can find, of course, the proper boundary conditions, is guaranteed to give me the correct wave functions and a correct charge distribution and so on outside the cores. It's what we call the pseudo potential. So it's not the potential itself. The word pseudo means I'm mimicking inside the core the real potential with something smoother, but I require to have the correct behavior outside the core. So in practice, what do? We take, say, silicon, we take an isolated silicon ion, we do Hartree-Fock fancy calculations and calculate its spectrum, good, so we know what we want. Then we start playing around with some model potential, which has some particular algebraic form, depending on a few parameters, and I play with these parameters until, by doing some DFT calculation, DFT-like calculation for an isolated atom, so using exchange and correlation energy that I will use in the calculations for my crystal, I calibrate these various parameters of this potential so that I can reproduce the spectrum that I've obtained from the more correct and more complicated Hartree-Fock calculations. Having obtained that, then I port it to the crystal. Since I've calculated the pseudo potential by accounting self-consistently for the charge of the electrons, So for the Hartree potential and exchange and correlation, because I've used the DFT-like calculations, then I can assume that porting into a crystal, I will obtain the correct results outside the core, because I've obtained the correct spectrum for the isolated atom. Of course, spectrum here only for the valence electrons. The core electrons, clearly, I will not have any information about because of the very definition of what the pseudopotential does. So that's the idea. Getting rid of all of the especially high frequency components of the potential, the ionic potential, the lattice potential, and of course of the wave functions. Once I've calculated the total spectrum of the Hamiltonian, I get rid of the high frequency components so that the size of the matrix that I have to deal with, the eigenvalue problem that I have to solve, is manageable. And typically for a bulk FCC crystal, I will now discuss what the difference between empirical and self-consistent pseudopotential. Usually if you use empirical pseudopotential, you get down to a rank of about 100. 100 G vectors are sufficient to capture most of the information that you need. If you do self-consistency, since you have a little bit more sensitive, well, you are sensitive to the charge distribution, you want to capture some variation on the charge more accurately, and typically the rank of the matrix that you have to solve is as large as an order of magnitude bigger, about several hundreds to 1,000, but no bigger than that. Compared to the million that we started from, that's very useful. So this is the concept of pseudopotential. Here is a lot of words. Let me tell you what it says. We have two different ways to deal with this object, with the pseudopotential. One is the way I just told you. So I calibrate it to the isolated ion, but in a self-consistent way. So I calculate my model potential to this model potential that I'm fitting to data. I add the Hartree potential, which is the mean field that one electron out of my 4 valence electrons or my isolated silicon fills the potential of the other 3 electrons in a self-consistent way. I add whatever exchange and correlation energy I need to add, might be the local density approximation. So my exchange and correlation functionals will become proportional to the cubic root of the density of all of the electrons. I solve by Schrödinger equation. Clearly, this is not as simple because it becomes a nonlinear integral differential equation, but I solve it by iteration, for example. And that is a self-consistent way. And then this pseudopotential that I've calibrated to my silicon atom, I port it to the crystal. The alternative is to say, let me just be as naive as I can. I will just lump into my pseudopotentials an empirical form that I'm using to calibrate the empirical pseudopotential. I lump everything into it. The Hartree potential, the exchange, and the correlation energy, all of them are lumped into this empirical formula, which depends on 3-4 parameters that I tweak so that I can obtain the correct band structure of the crystal. So this is essentially the basic difference between self-consistent and empirical pseudopotentials. What are the advantages and the disadvantages? Self-consistent pseudopotential, you're using density functional theory. We know the density functional theory, even if we use the Kohn-Sham local density approximation, we miss the gap. It's not just a gap. I remind you the density functional theory is a ground state theory. The Hohenberg-Kohn theorem guarantees that the electronic properties of the system are a function now only of the electron density, only as far as the ground state is concerned. Excited states, we have no right to expect anything good. And indeed, there is this problem of the band gap. It's more than that, it's the entire conduction bands, which sometimes is a little bit mistreated. Usually it is kind of compressed. Everything is compressed energy-wise, so you get a slightly higher density of states than you should have. So there are some slight issues. If you're interested only in balanced band properties, typical the atomic configuration, for example, it's excellent. But for the conduction band, there are issues. So the pseudopotential that I calibrate in the self-consistent way are portable. meaning that if I'm interested, for example, in studying strained silicon, I compress silicon, I stretch it in 2 dimensions, for example. If I consider silicon nanowires or a silicon thin film where I'm missing at the surface, I'm missing ions, the ions in principle will rearrange themselves. The electronic charge distribution in the valence band will change. So the screening on the potential, on the pseudo-potential itself will change. So doing that calculation consistently, I can capture all of these effects. The empirical, once I calibrate my empirical parameters to something, to the bulk silicon, that's it. These are valid only for bulk silicon. The typical example is if you're studying 3,5 compound semiconductors. Let's say I'm studying indium arsenide and indium antimonide. Indium is indium. If I do a self-consistent calculation, I will use the same semi-pseudo-potentials for indium in both cases, in indium antimonide and indium arsenide. On the contrary, once I calibrate my empirical pseudo-potential to, say, indium antimonide, I do not expect that the same indium empirical pseudo-potential will remain unchanged when I move to the other material, indium arsenide. And that's because the valence band, the valence electrons will be distributed differently in the 2 materials. So self-consistent and the pseudo-potentials are portable. They permit, of course, they have a higher predictive power. I can study relaxed structure. I can actually relax the ions and see, for example, what is the lattice constant that I get from the theory, something that I cannot do with empirical pseudo-potential because I fix my ions at their equilibrium position, given experimentally, for example. They are portable, but I get incorrect results about, unless I do something about the band gap and the conduction band. We mentioned before already that you can go beyond the local density approximation using the generalized gradient approximations. You can use hybrid exchange correlation functionals, which is even the pseudo-potentials themselves. There is a zoo of pseudo-potentials. I don't know if you're familiar with DFT calculation. You can choose the pseudo-potentials themselves. Ultrasoft, the Vanderbilt, or the Peter Blottel pseudo-potential. So there is a huge literature in improving the efficiency of the calculations by choosing suitable self-consistent pseudo-potentials. The empirical, well, what you get is you get the correct band structure by definition because you fit to them, not portable. So if you're studying strained silicon, you have to do something more than just looking what you've done. Now, the interesting thing is, I told you we're, say, for empirical pseudopotential, we're fitting them. Boy, to fit the entire band structure of a solid, of silicon, how many parameters do I need? The amazing thing, which tells you that the physics is basically correct, is that I do not need that many parameters. And actually, the amazing thing is that in order to calculate the entire band structure of silicon or germanium or diamond, all I need are 3 numbers. 3 parameters are sufficient. If I move to ionic semiconductors, like 3,5 compound semiconductors, well, I have 2 ions, so I need, not surprisingly, twice as many numbers, 6, or 3 complex numbers, whatever you want to put it. So the calculation of the band structure actually requires a lot of fitting, yes, particularly if you're dealing with the self-consistent calculations, and a lot of calculations to reproduce the valence band, the valence spectrum of the isolated ion. But the power of the theory is tremendous because you get a lot of information out of very few parameters. What I'm showing here, for example, is the empirical pseudopotential for silicon. These are the Fourier components. You see how it decays very quickly for large Q. That was the idea. We want this thing to go to 0 extremely fast. Actually, most of the forms that we have for the pseudopotential is empirical expressions. Maybe next week I'll give you a form, one of the many parametrized forms that people have used in literature. This thing decays exponentially with Q square. So it goes to zero very fast. Again, this is the reason why we're using pseudopotential. We want to kill all the high frequency, especially high frequency components. And then it goes to zero. There is a general statement that has been discussed, argued against a little bit, but I'm in favor of it. You know what is essentially the average ionic potential. You know it from Thomas Fermi screening theory, and that's about minus 2/3 the Fermi level of your crystal. So you know how many electrons you have per unit volume. Treat them as free electrons. This gives you Fermi energy, and the value of the pseudopotential at Q equals 0, which is the average ionic potential, is negative, of course, because the crystal stays together. The electrons stay inside the crystal because the overall potential is attractive, and you know what this value is. And then you have to play a little bit with the form that you have. Now, for a bulk crystal, actually in one of the problem sets, I think is the first one that I assigned, or the second, I forget, you're asked to calculate all the G vectors for an FCC crystal like silicon, so all the reciprocal wave vectors. And you see that the first ones, in units of 2 pi divided by the lattice constant, the first ones, well, that is the vector 0, 0, 0, which is the first G vector. Then you have 8 vectors, which are 1, 1, 1, with all the possible sign permutations because of the cubic symmetry of the crystal. And these are the G vectors that have a length of square root of 3. So sometimes we call it square root of 3 or G squared equals to 3. In units, of course, of 2 pi divided by the lattice constant, 2 pi by A. Then you have these vectors, which have a 2. Essentially, you can form now, these are the primitive translation vectors in reciprocal space. I gave you the formula 2 weeks ago. So you can now form all of the G vectors by adding linear combination, integer linear combinations of these vectors. So the first one that you get is the 2, 2, 2. And you have 6 of them, 2 from here, 2 from here, 2 from here. Sometimes these are called the star of the vectors 2, 0, 0. These are all of length 4, square length 4. Then you have the 2, 2, 0, the 1, 1, 3, or 3, 1, 1, whatever, and so on. So these are the first G vectors that you can find out of the formula that I gave you some time ago. So you need, going back to what we had here, so in your matrix now, you need these objects, the Fourier components for all of the G vectors. This G prime actually is a G minus G prime from the way we defined it here. It's a definition of the Fourier transform. So essentially we need, let's go back to where we were here. So we need to find we need to know the values of the lattice, the Fourier transform of the lattice potential only at these values in reciprocal space. And typically we call it V3, V sub 3. This means the Fourier component of the lattice potential for any of these 1, 1, 1 vectors. The V4, the same for the 2, 0, 0 vectors, the V8, which are the 2, 2, 0 vectors, V11, which are the 1, 1, 3 or 3, 1, 1 or 1, 3, 1 vectors, assuming that it's spherically symmetric. We're starting from actually from the solving the problem of getting a potential for an isolated ion looking in the presence of the core. The core is a closed shell, so you can assume spherical symmetry for the potential. Of course, the wave function will not be spherically symmetric, but the potential is. So typically, by the time we get to the 4, 0, 0 vectors, we are somewhere here. It's very small. 4, 0, 0 actually is 16, so we're very far away. So we can ignore it. So essentially, we need to know only 3 numbers, which are these 4 numbers, V3, V4, V8, and V11. For silicon, we have only 1 ion, so we need 4 numbers. For 3, 5 compound semiconductors, we have 2 ions, so in principle, we need 8. Actually, we need 1 fewer than that. The reason is that if you go and calculate for silicon, what is this form factor, structure factor, for when G minus G prime is one of the 2, 2, 0 vectors, so square root of 4 is their magnitude, you find that actually this by symmetry, where this tau r is 0. So V at 4, V of 4 doesn't have to be 0, but it doesn't enter the calculation at all. Similarly, if you go to a 3,5 compound semiconductors, you find that the sum, this object here, now we have a little more complicated sum because the ion depends on alpha. Could be gallium or arsenic, for example, for gallium arsenide. So if you go and look at what is the combination that you obtain when this G minus G prime is equal one of the 2, 2, 2 vectors, you find that also this form factor vanishes because of the symmetry of the crystal. So actually what happens is that for silicon, diamond, germanium, the V, where is it? The V4 doesn't enter, we don't have to know it. So we need only 3 numbers, V3, oops, sorry, V3, V8, or V11. For gallium arsenide, we need actually the V3, V8, or V11, the symmetric combination bit of the sum of the gallium and arsenic pseudopotential, for example, and we need 3 more for the antisymmetric combination. So in practice, we need 3 for zinc blende type, for diamond type, and 6 numbers for zinc blende. I find this quite amazing, that you can actually reproduce the entire band structure with so few empirical parameters that you need. Now, before showing you some results, let me keep up one of the promises that I made, which is how do we go from orthogonalized plane waves to pseudopotentials. So far, what I've done is say, well, I'm fitting these parameters, right? I'm looking for just 3 numbers, or if I want to study, for example, strange silicon, if I want to study something else, I may want to know the full dependence on Q. This requires a few more parameters, but this is an empirical model. It's, if you want to call it, it's very brute force. So I find some value, that some form of the pseudopotential that gives me the correct band structure. But really, yeah, I mean, the physics is correct. We know what we're doing. We want to truncate the high frequency components of the potential, the ionic potential, because of the reasons that we explained before, which are physically correct. We know what this has to be at Q equals 0. With someone will argue, but I claim that we know what it has to be. So I have some constraint, and then I can play around with my numbers and see what I get. There's no physics behind it. Moreover, I'm missing something. And that's the fact that a projection, remember that we are projecting the full wave function on a subspace which is orthogonal to the subspace of the core states. So there are some integrals involved. The projection means I'm taking the dot product of my full wave function with the core states. The dot product in a Hilbert space is an integral, right? So I'm doing something which involves integral, which implies that I have some non-local components. So the potential is not just a local potential, as I wrote here. Let's go back here, where we started from. Here, okay? I write it as a local potential, as if I were dealing with a regular Schrödinger equation. There's more to it. So this is what Harrison did. So remember where we started from. This is a projection operator. I hope that this is familiar for everyone. If it's not, please let me know, ask a question, interrupt me. Suppose that this is a complete set. Remember, this T is the set of eigenvalue of quantum numbers that label the core states. So NLM, for example, for an isolated ion. Alpha is just the ion number. If I were to consider all of them, not just the core, all of them, this would be a complete set of basis functions that spans the entire Hilbert space. Therefore, well, yes and no. I would have to add the continuum too. But if this is a complete set, this is just the identity operator. Applied to a wave function says, take its Fourier transform and for each Fourier component multiply by, say, a plane wave. So this is just the identity operator. If I'm limiting to a subspace, like the core states in this particular case, for silicon I'm using, for example, T is only 1s, 2s, and 2p. The 3 are the valence states, so I don't consider them. So this is the operator that projects any element of the Hilbert space that I'm dealing with onto the subspace of the core state. So the orthogonalized plane wave can be written as, well, take my block wave function and subtract out the projection. So I project it onto the space which is orthogonal to the core states. So the idea is, what does pseudo wave function psi that I can define this way, what equation does it satisfy? So all I have to do is take this object, replace it into my original Schrödinger equation, and I do a little bit of a few manipulations. At the end, I find a Schrödinger equation, which is like this. Notice, maybe I apologize for the strain notation. Notice that this is not a V of r times phi of r. It's not a product of a function of r, of the position coordinates, times the wave function. It's really an integral. It's this object. I'm projecting out the wave function from the core states. So in my manipulation, I get this term here, and I have to apply to the wave function. So this will be an integral. Okay, it's essentially written here. So the pseudo potential has a non-local component. This is a little messy because now my Schrödinger equation, I think I've written it explicitly here. Yes, this is the explicit form of my Schrödinger equation. These are the eigenvalues corresponding to the core states, or the energy of the core states, if you want. These are the wave function of the core states that you can, in principle, calculate from Hartree-Fock calculations, for example. And then you see that I have a differential operator acting on my unknown, but the unknown now enters as an integral. So this is an integral differential equation. This is integral over the entire volume, the normalization volume. Okay, so it's a integral differential eigenvalue problem. So it's a little messy, but this is how the concept of pseudo potentials comes about. So it's a non-local operator which will have a local term. This will be the term which will account for also the Hartree component of the core electrons and so on. So I'm getting rid of those, but there is a non-local component. And that's actually, I'm not sure historically which one, the model potential or the pseudo potential, which was devised first. But if you look at empirical pseudo potential, for example, the first paper that presented some realistic results for zinc blende and diamond type semiconductors, I think they consider 12 materials. It was by Cohen's group, the students Bergstrasser, and it was in 1967, I think. They use only the local part. They ignore the non-local component. About 10 years later, 1976, again in Cohen's group, they derived they calculated the band structure using also some good model, physically based model for the non-local part. And they added also spin orbit interaction, about which we will talk. Maybe not today. I hope so, actually, later on. So this improves the energy range in which the empirical pseudopotentials give you good results. So not just around the band gap, or just an electrovolt or two. If you use non-local corrections, then you push up the energy in which the model gives you good results. Okay. So this is a computational example that I told you. Oops, let me get rid of this stuff. So for silicon, germanium, gallium arsenide, actually the best idea is to consider, remember that the two atoms are at, I don't have the plot in these slides, but I showed you last week, we have two ions per unit cell. One is at 0, 0, 0. One is at 1 quarter, 1 quarter, 1 quarter in units of the lattice constant. Actually makes more sense to take the origin of the coordinate system midway between the two atoms, So one ion will be at plus 181818. The other atom will be at minus 181818, minus all three. So you get a symmetric thing, and then you can look at the expand the form factor. This is the expression that we had, if you remember. Let me go back here. Okay, here we go. I'm writing this sum. Now I have two ions in general, if I consider, for example, 3,5 compound semiconductors. So we'll have e to the I g tau 1 times v1 plus e to the minus I g t2 times v2, where 1 or 2 are the ionic pseudopotentials for ions 1 and 2, gallium and arsenic, indium and antimony, whatever. So what we do is, this is the same form, now explicitly written down, very simple because I only have 2 ions per unit cell. And these are the Fourier components of the ionic potential, pseudopotential of ion 1 for the wave vector, G wave vector. Now, if I have a FCC crystal such as silicon and gallium arsenide, as I said, I can put the 2 ions at 18 plus or minus 18, and I can rewrite this expression. Since tau now, tau 1 is minus tau 2, I can just call it tau. You see that I can rewrite the empirical pseudopotential, the Fourier transform of the empirical pseudopotential in terms of a symmetric part, where I have the sum of the 2 potentials, and an antisymmetric part, which is also an imaginary, if you want to write it in imaginary term. Okay, so my Hamiltonian matrix will be a real symmetric matrix, real, when the 2 ions are the same, because this term is, say, V silicon minus V silicon. It dies, it's killed. If I have gallium arsenide or indium antimonide or whatnot, then I will have a complex Hermitian matrix. And so my eigenvalue problem is a little more complicated. The rank is twice as big, if you wish. So for silicon, for example, notice that, as I told you before, I only need 3 parameters, which are the V of silicon at only 3 values of the G vectors, where the square of the G vector is equal to 3, to 8, or to 11 in units of 2 pi by a. And that's because the structure factor of one of these G vectors is 0. The results that you get are really impressive. What I'm showing here is, look at the dashed lines. You reproduce the valence band. By the way, these pseudopotential were calibrated to experimental data that tell you what are the energies at the symmetry points. You can get that from electroreflectance data. Optical absorption gives you the joint density of states, so it gives you in some way the energy difference between, say, what you have at the L point or what you have at the gamma point, the direct energy gaps. So they're being calibrated to a wealth of experimental data. And look at just at the local pseudopotential. Yeah, you see that there are some differences that I mentioned before. The non-local pseudopotential give you actually better agreement at even higher energies. We'll talk about the tight binding. This is a tight binding model in red. We'll talk more about it. So an impressive amount of data that you can calculate. These are fit to, say, the entire absorption spectrum, optical absorption spectrum, the entire electroreflectance spectrum. I would say you can calculate even the dielectric function, the real part and the imaginary part of electric functions. All of this information out of 3 numbers. So clearly the physics is good. This is just the density of states. We'll talk more about this. For germanium, germanium was historically the first semiconductor of interest. It was also a little bit unfortunate that germanium has the minima of the 3 values in the conduction band are very close together in energy. The minimum at L, the minimum at gamma, the minimum at X. Actually at X we have 8 minima, so 6 minima, 8, and L we have 8, sorry, this is 6. For many years people actually didn't know which was the correct order. It wasn't clear whether germanium was a direct gap semiconductor, whether the minimum was away from gamma at the symmetry points L or X. For silicon, you know that the minimum is somewhere close to the X point. So this is the 1, 0, 0 point in the Brillouin zone, and the gap is indirect. For germanium, it wasn't clear. I don't remember actually when it was established that what is the correct order. Now we know that the difference in the energy point at gamma is about 190 millivolts, if I remember correctly. It is a little bit bigger at this point, close to the X point. Gallium arsenide is clearly direct gap, like many of the 3,5s. Not all of them. Gallium phosphide, for example, is indirect. Some of them had a minimum at X. And that's why it's all the direct gap materials are extremely interesting for the optical properties and what you have. Indium gallium arsenide quantum wells in your DVD players or whatever. Okay, DVD is blue, so it's not exactly gallium arsenide. Okay. Any questions so far? Am I still online? Do I exist? My usual question midway to make sure that you hear me, that I'm okay? Yes?
Yes, Professor.
Good. Okay. Yeah, let's go on a little bit longer. And then, let me get back to my pointer here. Before getting into the competitors, which are the methods to calculate the band structure which do not rely on plane waves, but rely on a set of basis functions which are atomic orbitals, so localized orbitals. I want to briefly discuss the K dot P rather than method, I should say perturbation theory. It's a way to get some semi-quantitative ideas about what we expect from a band structure, in particular what we expect from effective mass. The idea, for example, that if you have a small band gap, you're going to have a small effective mass and vice versa. That's an important result out of perturbation theory, that bands repel. That's another general result that we'll see for many other types of dispersions, of other elementary excitations, not just electrons, but also phonons, also plasmons, also interface plasmon-phonon modes, and so on. So it's a general property. This is the K dot P method, which is actually useful as a good way to treat some situations like the valence band of these materials, the FCC crystals, is actually quite complicated. And the best model that I can think of, the simplest that preserves the basic features, the basic physical features of the band structure, is this K dot P method. What is the K dot P method? Well, let's go back to our Schrödinger equation. Phi lat is whatever it is. I'm not making any assumption about what is the lattice potential. This is the equation that we have. We know that the wave function has to have a block form because of Bloch theorem. So I simply plug back my block component into Schrödinger equation. The exponential of the plane wave can be factored out, disappears, and I'm left with a differential equation for the u. Notice that I call it a differential equation because this p, the momentum, is actually the Laplacian. Okay, well, it's the gradient. So it's really a differential equation. But written in this form tells me something. Suppose that somehow a friend of mine did the full calculations with DFT or whatever and can give me all the information about what are the u's, so the eigenfunctions or the eigen pseudo wave functions at some particular k point. Say k equals 0 is the typical point that we will choose, which is convenient and simplifies the notation. So let's take it k0 equals 0. Suppose that we know everything. We know the u's, which means that this friend of mine has solved this equation. Okay, k equals 0 because we are setting k not equals 0. So at k equals 0, at the gamma point, we know everything. We know the eigenfunctions, the u's, and we know the eigenvalues, which are the various bands at gamma. And n labels the various bands, the various eigenvalues, eigenpairs that I have. Now, let's look at this equation, and let's assume that I want to treat k as a perturbation. So I want to move away from the point where my friend did the calculation, k not equals 0, a little bit. So what I can do is expand the square here. I will have a term which is the p square, which is this guy. Then I will have a first term which is the k dot p, which is where the method takes its name from, which is this term. And then I have a second order term, which is the square of the k, the kinetic energy. Okay. Now, most of the cases, if I'm expanding around gamma, for example, if I go away from the gamma point, k equals 0, in one direction, by symmetry, if I go along the 1, 0, 0 direction, I have to find the same result that I get around the minus 1, 0, 0 direction, the opposite direction, because of the symmetry of the crystal. So the first order term instead would give me something that changes sign if I go from a positive direction to negative directions. So that cannot be. With some rare exception, the first order correction that I get from the perturbation term, or what I consider now a perturbation term, will vanish. So I'm left now with second order corrections, which will be the second order term that I get from the square of this object, and second order perturbation theory should be used to consider the second order term in this form. So what I have is, by using second order perturbation theory, time independent perturbation theory, so stationary states, will be that my second order energy will be whatever energy I have, which will be this E0 for my bands. Okay, this will be the 0 order. And then I have the second order correction. Again, the first order disappears, vanishes. So I have simply the matrix element of this term, which is diagonal. So I just pick up this term. And then the expression for second order perturbation theory in the k dot p term. And so you see something interesting. Notice that p is proportional to k squared, essentially to k is the crystal momentum proportional to that, some simpler cases. So what I can write, for example, is I can rewrite this expression as a correction which is similar or reminds me of what is the dispersion of a free electron. Remember, a free electron is a k squared over 2m. So I want to lump all of this stuff, rewrite it in this way, okay, where ki and kj are the components. I and j runs about around x, y, z, the three Cartesian components of the k vector, in terms of a parameter called m star of ij, which actually happens to be a matrix, or a tensor actually, which I call effective mass. And the definition of effective mass, if I want to make this look like this, I have to define the effective mass implicitly via this relationship. It's a delta ij, because clearly I get this term, which is the k squared. And then there is a correction, which involves the matrix elements of the momentum operator, the components of the momentum operator, over the periodic component of the wave functions at the point where the friend of mine told me what they are. Remember, we're starting with the assumption that we know what these are. If we don't, then we can treat them as empirical parameters, which is what usually it is done, actually. The calculation of this momentum matrix element is quite complicated because you have to know the use. Typically, you will have to rely on DFT, for example, or empirical pseudopotential. But anyway, you must have information about the periodic component of the block wave function. One interesting thing is if you look at this term, which defines the inverse effective mass, notice that the biggest contribution to the effective mass is given by terms which have, sorry for my clock, 10 o'clock. Okay, we're done. No, not yet. Okay. So the biggest contribution to the effective mass is due to bands. Remember, here we're summing over all of the bands at gamma, which is where we have information about the wave functions. The smaller denominators gives the biggest contribution. So nearby bands contribute the most. In particularly, I'm summing over the bands. I'm calculating the effective mass for band R, say conduction band 1. I'm summing over the bands. You see that bands which are below the conduction band, band 1, give me a positive contribution. Okay, bands which are above the bottom of the conduction band, higher bands, give me a negative contribution. So this is the typical results that we get from second-order perturbation theory, that bands repel. If I fix a band and look at some perturbation that changes the band structure, all of the contributions of the bands which are below push my eigenvalue up. All of the contribution of the bands which are above push my band down. So bands tend to repel. Again, this is a general result out of second-order perturbation theory, if you wish. And notice also that if I have a very small contribution coming from the nearest band, say indium antimonide, which has a very small band gap, the band gap is much smaller even than the difference between the highest energy valence band and the one below. So the biggest contribution to the effective mass comes actually from the conduction band in the valence band. And you see that this can be pretty small. So you have a large contribution to this, but this is proportional to the inverse of the mass. So a large positive contribution gives me a small mass, a large 1 over Mij. Okay, so you see that the effective mass is essentially goes hand in hand with the band gap. If I have a situation in which the biggest contribution of this sum to this sum comes from the direct gap that I have in a semiconductor. So this gives me some idea about what to expect for the effective mass in a solid. If I have a large band gap material, silicon dioxide, the electron energy, the whole effective mass actually is huge, somewhere between 5 and 10. The electron effective mass is a little smaller. If I have a very small band gap material, the mass will also be very small. So for gallium arsenide, where the band gap is about 1.4 something, I have a mass of about 0.06. Remember that in silicon, I have to consider here the direct gap. So the band gap for silicon is of the order of 3.2, 3.4 electron volts, averaged over the entire Brillouin zone. For indium antimonide, where the band gap is less than 0.2, I think, the effective mass is 0.02, something like that. So there is this relation that can tell you immediately when to expect a small effective mass. This method, as I said, has been used a lot also when you have degenerate situation. I remind you that in degenerate perturbation theory, you can get some information. You have a problem, of course. If R and S are degenerate bands, then this thing blows up. You get a singularity. The way to deal with it would be to diagonalize this matrix. So if I consider the first 3 valence band in silicon or gallium arsenide, in principle they are degenerate. Ignore it in a spin-orbit interaction that we'll talk about. I have to diagonalize the matrix element of the momentum operator in the subspace spanned by the 3 eigenvectors corresponding to the top of the top 3 valence bands. I diagonalize it, and then I can use degenerate perturbation theory to deal with the problem. This is something that, for example, has been done by Kittel and co-workers, Dresselhaus, I think it was Mildred Dresselhaus, Hip and Kittel, for the case of the 3 valence band in silicon and germanium. This is a very commonly used approximation. These parameters L, N, and N. Of course, you can calculate them using DFT, for example. At the time, they treat them as empirical parameters, and the symmetry of the crystal tells you what you have. So this is essentially the Hamiltonian that you have, the matrix in the general perturbation theory that you have to diagonalize in order to get the eigenvalues. These are some results. For example, using K.P perturbation theory, this is for relaxed in the middle and strained silicon, compressively strained biaxially or instead on the tensile strain. We will discuss spin-orbit interaction, but you see that you have 3 valence bands which have the highest energy, 3 valence bands. You have 4 valence bands in this material because you have 4 atoms, two atoms in a unit cell, each of them with 4 atoms, so you have 8 atoms, so you expect 8 bands. However, if we lump spin into these bands, we multiply by 2, so we end up with 4 bands in which the electrons can accommodate each 2 electrons with spin up and spin down. The spin-orbit interaction actually splits the bands, but you see the general feature. You see what I mean by bands repel. For the strain case, is particularly interesting. This is what is called the heavy hole band, the lowest curvature, which means the largest effective mass. This is what's called the light hole band. This is the split off band. The fact that the bands repel can be seen in the strain cases in which actually bands would like to cross in some particular case, but they do not, and they repel, as I said before. So keep in general these features in mind. I think that this is for, I'm not sure what the difference is between these two. Anyway, trying to understand. Okay, anyway, this is a general feature. You have 3 bands, and the valence band, the top 2 are the heavy hole and the light hole, and then you have a split off band, and that's what we will discuss later on. Okay, let me finish this first part of today's lecture dealing with the, I keep saying competitor, with an alternative way. I think I mentioned before, I'm a fan of plane waves because at least I keep my peace of mind. I know that I will have to make a little more effort, but the results that I will get will not be biased in any way. Tight binding is the different approach. I use a different basis of functions. Clearly, any complete basis will do, and there should be no difference. The issue is depending on the basis of functions that I use to expand my unknowns, which are my wave functions, the number of basis functions that I have to use can change. And clearly, I would like to use the smallest possible number. So plane waves in reality deals very well with extended states by definition. If you want to look at bonding, and so the states that constitute the sp3 binding among the various silicon atoms, you really need several plane waves, and that's why you need at least 100, 120 with empirical pseudopotential. You need more if you do some consistent calculations. So it's a relatively large number. Or the order at least 100, if not several hundreds. In several cases, this is a excessively large number, especially if I want to deal with electronic transport, in which I have to combine several of these matrices to build bigger matrices. And these matrices will be sub-blocks of large matrices. So if I start with big matrices as sub-blocks of even bigger matrices, I will be able to I will not be able to deal with the problem in a very efficient way or at all. So the idea is, why don't I use the fact that I know already what the bonding wave functions look like? They're sp3, right? I keep saying about sp3. So why do I want to use plane waves when I know that essentially I will deal with sp3 orbitals? So it makes a lot of sense to think that way. The idea was originally due to Slater. And he said, why don't I do this? These are our core states, right? They used to be our core states. Well, let's go beyond that. Use the same notation. Alpha is the index that labels my ion in a unit cell, or in general. This actually is not in a unit cell. It runs over all of the ions. T is a set of quantum numbers that labels the atomic orbital. For silicon, I will consider the 1s, the 2s, the 2p, and now also the 3s and 3p. I'll consider them all, and I may even go further up to the 4, including the d orbitals, and so on. So these are the atomic orbitals. Let's consider a linear combination. So I want to express my unknown, which is my wave function, as a linear combination of atomic orbital. This T labels the atomic orbital, but I remind you, it will map into the bands, if you remember the heuristic discussion that I gave you about where the bands come from. So I want to construct my wave function as a linear superposition, not of plane waves anymore, but of atomic orbitals. Of course, Bloch's theorem still holds. I mean, even if I decide to use a different representation, so I must be able to express this as the term of a Bloch function. And indeed, I find that these coefficients, my expansion coefficients, have to have this form, again by group theory. They have to be a phase, only a phase. Remember, this has to be periodic. The square of the wave function has to be periodic because it's a physical quantity. So it has to be a phase, and the phase has to be proportional to the k vector. And these are my atomic orbitals. This normalization factors is a little tricky. I'll mention it in the next slide. If I use n orbitals, I will have to divide by the square root of the orbitals. You realize that this is a little, it's an approximation. If the orbitals are completely non-overlapping, then when I take the square of this wave function, it will be the sum of the square of each orbital. No cross terms will appear. So this is the correct normalization factor. If the orbitals overlap, they're not orthogonal, strictly orthogonal, then depending on the alpha that I use here, then I have a little bit of an issue. We will ignore it, but it should be kept in mind. Okay, so what do I do now? Remember, when we were using plane waves, what we did was go back to the Schrödinger equation for a singular electron, Schrödinger-like equation, plug the Bloch functions into that equation and see what we got. We'll do exactly the same here. So we'll plug this into our Schrödinger equation, keeping in mind that these orbitals satisfy the Schrödinger equation for a single ion, right? This is, let me assume, just silicon. So this is the ionic potential or pseudo potential or whatever for silicon. And these are the isolated silicon. And so this is just the equivalent of the hydrogen atom Schrödinger equation that I have. And this gives me all of these atomic orbitals. So we plug back this expression of my Bloch function, but now expressed into a linear combination of atomic orbitals. I plug it into Schrödinger equation, remembering that the lattice potential is given by the sum of all of the ionic potentials. Again, alpha is not restricted to a single cell. It runs over all of the atoms in all cells. So I do a little bit of algebra. I plug it back here. I remind you that we have to keep this expression in mind, and using this, we find that indeed we can express the Schrödinger equation in this form. A good, simple way to deal with the problem is to say, okay, let me calculate the expectation value of the energy that I have in this state phi. So what I do is I take this Hamiltonian and I calculate the expectation value. So this is the sandwich between this Hamiltonian that I have here and the wave function. And this will give me the energy versus k relationship. So will give me the band structure, okay? And again, this is this normalization that, again, in principle, can give me troubles because, let me remind you what we have. If there is a non-zero overlap between orbitals corresponding to different ions, to different alpha, then it's not just going to be a simple normalization that I have here. And we'll ignore it. We'll consider that this is 1, but it's a little delicate point. So what we're doing now is plugging back this expression for the Hamiltonian and the wave function. I get a sum, I get ET, which is the eigenvalue, the energy of the t orbital in the solid. This comes directly from here, from the fact that I have a sum of the lattice potential and I have that each of these size of t is an eigenvector of this operator. So I get the eigenvalue that I had in the isolated ion. Again, if you remember the discussion that we had when I was bringing two silicon ions together, say we have the 3s and 3p orbitals, and the energy of the bands actually comes from there. So we indeed start from the energy of the atomic orbital, but then we have corrections that in principle depends on k, which gives me the E versus K dispersion, my band structure, if you wish. Now, this is an integral over three terms, or I have for a given wave function here, I have a sum over the ions alpha that enter this expression, this expansion of the wave function over the atomic sites. I have a sum that I think I'll call sum over beta that I have over here for this wave function, and then the lattice potential is expressed as a sum also over ionic positions, and I call it gamma. So I have the sum over beta, alpha, beta, and gamma of various things. So I have a sum over alpha for the wave function that I'm dealing with here, a sum over beta, and then the sum over gamma for the ionic potential. The term e to the ik r alpha minus r beta is coming from the expansion over alpha of this guy and over beta of this guy, okay, because of this term over here. Now, the idea is I have a three-point integral here, so to speak. So for a fixed gamma, for example, I have to consider the ionic potential surrounding the ion gamma, and then I have to calculate the overlap integral of this potential with a wave function centered around the orbital, centered around ion beta, and centered around ion alpha. So the major approximation is to say that three body integrals do not give me any contribution. I will consider only two body integrals, and the idea is that they're weak, interacting weakly. Two of them already have a weak overlap. That's why we call it tight binding, because they are tightly bound around their cores, gamma, alpha, beta, whatever it is, so that considering now two of them, say beta and gamma, and consider a different alpha, will give me a yet smaller contribution that I can ignore. So we have different cases here. The case in which they're all different, I exclude. So I have to consider the case in which beta and alpha are the same, or the case in which alpha and gamma are the same. And then they give me different contribution. When I have alpha equal beta, which means I'm considering essentially the expectation value of the potential over a wave function in particular ion alpha, notice that the K dependence disappears because alpha is equal to beta, so this cancels out, becomes 1. So I have essentially the expectation value of the potential at ion gamma, average over all the other ionic position alpha. By symmetry, this cannot depend on alpha because of the symmetry of the problem. So this is nothing but the binding energy of the crystal, is the expectation value of the ionic potential over all of these atomic orbitals. And clearly it's not dependent on K. Terms in which alpha is equal to gamma are different. They give me now a K dependence. Remember, now we're taking alpha equals gamma over here. So this term is equal to this term. So I have the potential at ion alpha multiplied by the atomic orbital at the same ion alpha, and then I'm looking at its overlap with the potential at another ion gamma, an ion beta, sorry. So again, I have a term of this form. So this is, as I said, the potential at alpha, the orbital at alpha, overlapping at beta, and I look at what this overlap is. Again, by symmetry, it can depend only on, doesn't have to depend on beta. So what I have is the expectation value of the energy will be, again, the original eigenvalue that I had, which was the energy of that atomic orbital, times a term that depends on K, notice that this looks a little bit like the structure factor that we had from our pseudopotentials when using the plane waves. We had G vectors there. This is more general, but it's just a geometrical component. It depends only on where the ions are. And then there is a term instead that depends on the overlap between the potential and orbital at site alpha with another orbital. And they can put it in any place, right? A fixed arbitrary beta because I'm summing over all the alpha. Okay. So this is what sometimes is called a hopping term, hopping energy, hopping integral. It's really the overlap between the wave function and potential at one position and another one, or the wave function, if you want, the orbital at one position, and then multiplied by the orbital and potential at another ionic site. What can you do here? Well, you can simplify. In principle, I have to sum over all the other ions in the crystal. So it's an infinite sum. In practice, we already said that these are tight functions. They're localized around their site. So usually what people do is they consider what is called the nearest neighbor approximation. For a fixed R, I consider only the nearest neighbors to that ionic site, where the overlap between the atomic orbitals will be the strongest. You can improve, you can go to the next nearest neighbors and so on with additional numerical complexity. So the situation is that now we have, in generalizing, when I consider, so far I've considered only one atomic orbital, size of T. Let's consider many of them. So what I have now, I consider a matrix. So I express my expectation value of my energy as a matrix represented over the basis of the atomic orbitals. And following exactly the same procedure, the dispersion will be given by this diagonalized, the diagonal part of the matrix. For every atomic orbital T, I have the corresponding energy of the atomic orbital in the isolated ion. And then there is a term, which is the kinetic energy term of the band structure that depends on these hopping terms. And I can, again, use nearest neighbor approximation or next nearest neighbors, and I can use as many orbitals as I think they're necessary. Of course, if I use all of the neighbors and all of the orbitals, so that including the continuum, so this set of wave functions here becomes a complete set, I go back to an exact representation. The idea is to reduce the size of the problem so that I can deal with a matrix of a rank which is reasonable. For example, I showed you here, somewhere here, what happens when I use only 4 orbitals, the 4 sp3 orbitals. There is a fake one that I'm going to discuss in a moment. It's okay. It's not perfect, and you see that you make some mistakes. So the number of orbitals that you use is going to improve clearly your approximation. Typically, you get good results. I don't know if I have a plot. If you use the also orbitals for FCC semiconductors, the p orbitals, the d orbitals, you already have 9 orbitals here. In addition, you remember that bands repel. So the fact that I stop at high energy at the p, ignoring the d, or at the d, ignoring the f orbitals, this means that the highest energy p orbitals in this case, d orbitals in this case, will have an excessive energy because the bands which are above them don't push them down. So typically what people do is they introduce a fictitious s orbital, which is called S star, which is higher up in energy, and its purpose, it's only that of compressing a little bit the band structure higher up in energy. I think I have some plots actually of the band structure, but if not, I will post them. I don't have, I will post them later on. Okay. And again, so this is a good model. However, notice one thing. If I consider an sp3d5s star, I have 10 orbitals. If I want to account for spin-orbit interaction and the presence of spin, which actually matters, we haven't talked about it yet. We will learn the second part of this lecture. Then we already have 20, a rank of 20. So with empirical pseudopotential, we typically have a rank of 100. Spin orbit can be done by perturbation theory. So we are not orders of magnitude away from what pseudopotentials give you. And if I want to be more precise and go to next nearest neighbors, then the size, depending on the geometry of the crystal, the size of the matrix that I will have to deal with increases further. So considering that hardware has got so fast so far, I mean, everybody has their own preferences, but the danger is that you are already assuming something about your result when you truncate an expansion of this sort. The typical failure that I've seen of the tight binding is the PZ orbital only treatment of graphene nanoribbons. PZ orbital nearest neighbors only. So use only one orbital, PZ. You actually have 2 atoms per in a unit cell, so you have a 2x2 matrix. Use only nearest neighbors, and you get the correct band structure for graphene, the Dirac dispersion. In nanoribbons, you're missing a crucial element, an element that actually had been known to chemists since Augustus Kekulé in the 1800s, studied the chemical properties of aromatic compounds, benzene and so on. And you miss completely a crucial effect which determines the variation of the gap with the width of a graphene nanoribbon. This is, I mean, you miss it completely. I mean, even qualitatively, it's totally wrong. So you need at least next nearest neighbors, and hopefully you need a little bit, a few more orbitals. This is the most dramatic failure that I've seen. In general, it's okay. The other issue that I have with tight binding is that you consider these overlap terms as empirical numbers to calibrate your bench structure to what you can calculate with other methods. You do not have information about the wave functions. Nowadays, people are using maximally localized Vernier function in order to get some information about the radial component of the wave function. You know the angular component, because SPD, they mean the spherical harmonics corresponding to these orbitals. But you don't have any information about the radial components, so you have no information about the wave function that you have to use to calculate matrix elements for scattering, for example. You don't have any information about the charge distribution. You only have information at the lattice sites, but not in anything about the bonding configuration. So if you do DFT tight binding, which is usually beginning to be done nowadays, you recover that information. But now you begin to add such a numerical complexity to the problem that I think you begin to compete. I should say the opposite, that empirical or that even self-consistent or empirical pseudopotential begin to be competitive with tight binding. Okay, I need a break also for my voice, so I'll stop here. Let's take a 10 minutes break if you're okay with it. So it's 10:30, which is 5:30. So shall we meet at 22? If you're okay with it, in 10 minutes? Okay, I hope we're all back. Okay, I'm sharing again the slides. Do you see them? Yes. So do you see my slides?
No, we don't.
You don't.
I don't, at least.
You don't. Let me try again. Let me try again. What about now?
Yes, Professor.
Good. Okay.
Yes, we can see.
I took it off and now, okay, good. All right. So where are we? We saw 3 different methods to calculate the band structures of solids. Each of them had advantages and disadvantages. Mainly, it's a usual competition between physical correctness and amount of work that we have to do to get the good results. What I said about tight binding, of course, is my personal opinion. I know that there are people who have been using successfully tight binding, and indeed, if you use a sufficient number of orbitals, and particularly you go beyond the nearest neighbor approximations, it gives good results. And now DFT tight binding has become almost the norm. I think that the group at Purdue who do quantum transport using non-equilibrium Green's functions at tight binding, now they are using results obtained from DFT tight binding, not empirical tight binding. So they have also information about the wave functions. So what I want to do now is to give an overview of what you get for the semiconductors that we're interested in, particularly those of the FCC crystal structure, face center cubic. We talked already about it quite a bit. I'll be talking about the Fermi energy, just to give a brief reminder of how you calculate it. I talked about it, for example, where is my pointer option here, laser pointer, how you calculate the Fermi energy, the Fermi wave vector in a crystal. I said, for example, that empirical pseudopotentials at the q equals 0, so at infinitely long wavelength, the average ionic potential has to be equal to minus 2/3 the Fermi energy. It's just a free electron model. So what you do is you fill the Fermi sphere, you count how many states you have in a Fermi sphere. Remember that 1 over 2 pi cube times the integral in dk is the sum over the k points that you have in a finite volume normalization. So 1 over v, 1 over the volumes times the sum over k is equal to the integral with a factor of 2 pi cube. The 2 is for spin, so this is the total number of electrons that we have. This gives us the Fermi wave vector, and this is clearly the electron density. If we know how many electrons we have 8 atoms per big cubic cell, or 2 atoms in a primitive cell for the FCC crystals. So we know how many electrons we have, and we can calculate the Fermi energy. And the Fermi energy is about 10, 12, 13 electron volts. A lot of Rydberg. The Rydberg is the preferred energy units, either the Rydberg or atomic units. There's a factor of 2 floating between the two. And so we have something around 12 eV for most of these materials. Indeed, if you look at the band structure of silicon, this is just the valence band. Remember, we have 4 bands. There are actually 8, because in each band you can fit 2 electrons. So it would be 8 electrons, which is indeed what you have from the 2 silicon atoms in each Wigner Zeit cell. And you see what the width of the valence band is of the order of about 12 eV, something like that. This is actually the energy scale is set so that the bottom of the conduction band at the minimum near the X point is equal to 0. And you see in particular what I told about the structure of the valence band. We'll talk about the spin-orbit interaction in a moment. So actually, if you go and look with a magnifying glass, what you see here is that this band over here, which is the split of band, is actually split. In this scale, it's about 43 millivolts, so you don't see it. In this plot is about the width of the line, but there is a split. Okay, where are the gaps coming from? Actually, I told you physically where they're coming from. Two different ways to look at it. We saw it as a broadening into a band of each the energy of each atomic orbital. We saw it as coming from the chronic Penny model, for example, mathematically, where that arises from the periodicity of, in that case, was one-dimensional periodic structure, one-dimensional crystal. You can do a simple analysis in perturbation theory. If we go back to the plane wave representation of our problem, remember this was the eigenvalue problem that we were solving. Eigenvalue because we can bring this E on the other side. So we get this matrix. These are the diagonal terms of the matrix. These are the off-diagonal terms. These are the eigenvectors, the components of the eigenvectors for a fixed K. As we move K around, we get the band structure, which is what I illustrate here, going from 0, 0, 0 to 1, 0, 0, and then in various other directions in the Brillouin zone. And what we can do is to consider, for example, what happens first in the empty lattice. The empty lattice means this is 0. And then clearly we have this result. Without the wiggle, if this is exactly 0, this is the dispersion that we get, which is the dispersion of a free electron in a folded or repeated zone. So we have just a parabola, and then when we hit the edge of the Brillouin zone, we fold over the band structure inside the Brillouin zone, and we keep reflecting it back and forth. So each band, each G represents a Brillouin zone, the first, the second, and so on. So this is what is called the empty lattice. So there's no potential, but there is a periodicity underlying this ghost potential that we set to 0. Then we consider perturbation theory, assuming that there is a lattice potential which acts as a small perturbation. So what we can do is to use first-order perturbation theory to express the first-order corrections to the wave function, to the eigenvectors, which is the sum over all of the other bands. This is the same expression that we saw from K dot P. This is the energy of one band, and that's the energy of the other band. And essentially, it's just the proportional to the matrix element of the closest band, picking up the smallest denominator for a particular band that I call little b. We pick up the next conduction or valence band, the closest one, and this is typically the leading correction that we have to the wave function. So it will be the wave function of the unperturbed next nearest band times this coefficient, which is clearly dimensionless because both numerator and denominator have dimension of energy. So if we plug it back here as in this term as second-order perturbation theory, we get this expression. Again, bands repel. We sum over all the G's. The G's which are below push my band up. In this case is A. If the G's are above, they push my band down. And now we can use, if we have a band which is degenerate, when we hit the edge of the Brillouin zone, clearly here we have two bands, the first G and the second G are equal at that point. So we have a degenerate value. And at that value, we have to use degenerate perturbation theory. So we have to diagonalize the Hamiltonian expressed as a matrix in the basis of those two degenerate eigenvalues. And just cranking up the numbers, this is quite trivial from second-order perturbation theory. We see that at the point where the bands were reflected, so this point here, for example, where am I? At this point, where I hit the edge of the Brillouin zone at the X point, this is the degenerate point, and I will open a gap, which is in this gap over here, which is proportional to the difference between the lattice potential at 1G and the other. Okay, so this is just a simple way to show where the gaps arise. This is approximated, assuming that this is small. Clearly, in a real case scenario, this is actually quite big, and we have big gaps which open up. I mentioned spin-orbit interaction already a few times. This is where I usually run into pedagogical issues. Here, and we may see it later on, I have to use some concepts that really rely on relativity. Usually, students of electrical engineering do not have a formal class in relativity. So I have an appendix that I haven't posted on the Teams group or the activity section or the files, I think, but I will, which deals with basic principle of relativity. It's interesting for two reasons. First, it helps understanding some of the things that I will say. In this case, for example, the equivalence between an electron which is moving in an electric field and the fact that actually the electron feels as if it were in a magnetic field, in the presence of a magnetic field. I think you've seen Maxwell's equations, and you know that there are some strange issues. One of the first questions that one may ask is looking at, for example, at the expression for the Lorentz force. That's great. I mean, an electron in a magnetic field feels a force which is of a magnitude which is proportional to its velocity, and it's perpendicular to the velocity. That's great. What if I sit with the electron and ride with it? In that case, the velocity goes to zero. So where does the force end up? Well, you know the answer, I hope. The magnetic field disappears. It becomes an electric field. This is something that Galilean relativity or Galilean transformations do not permit, do not account for. So we need something else. It tells us that the electric and the magnetic field are actually single objects. They're really not vector. They don't transform like vectors. They transform in a more complicated way. They're actually a tensor. And the transformations are not Galilean transformations, not just a reference frame which moves with one constant velocity with respect to another, and only the spatial coordinates transform. Time is also involved, and also time transforms. And that's because the magnetic and the electric field in Maxwell's equations are related, their time derivatives are related to the curl of the other field. The curl of B is equal to the time derivative of E, and vice versa. So you need to go beyond Galilean invariance. Minimal coupling, we will have to deal with optical processes. What happens when I shine a photon on a crystal? How does an electron respond in the presence of an electromagnetic field? And that will require what's called a minimal coupling, replacing the momentum of the electron with a quantity which is the momentum plus the vector potential of the field. Where is it coming from? Where is it coming from? It's coming again from special relativity. So the third thing is, I will probably next week, we'll briefly touch upon the calculation of the band structure of nanostructures, systems which are not periodic in all three directions. I mentioned before, thin films, quantum wells, nanowires. We lose periodicity in one or two directions, retaining it in the other, remaining directions. How do we use plane waves to calculate the band structure of these things? And we will deal with graphene as one example. And in graphene, people say the electron dispersion is well approximated by the massless Dirac equation. There's no such a thing. I really don't like the terminology, but we'll talk. So where's the Dirac equation coming from? So if you want to have an idea about why people talk about graphene in these terms, you have to know something a little bit about relativistic wave equations. Schrödinger equations are not relativistic. So where did Dirac get it from? spin. The Dirac equation introduces spin naturally into the formulation, while if you're dealing with Schrödinger equation, spin has to be added on in an ad hoc way. I just plug it in because that's what experiments tell me. There's no formal derivation. Derivation is probably not the right word. I don't want to go into philosophy of knowledge, but we have to add it somehow. Dirac equation introduces it in some particular way, but automatically. So I think I will spend at least an hour briefly discussing this thing so that we're on the same page. So spin-orbit interaction indeed can be explained in these terms. I stole this picture from the web, but anyway, you have your nucleus, you have your electron which is orbiting the nucleus in this simple Bohr-Sommerfeld idea. The electron has a magnetic moment, and that's because the electron is spin. The electron is a charged particle. If it rotates around its axis, as wrong as this picture might be, but it's kind of intuitive, it has a magnetic moment. And we'll talk about the fact that this is actually a strange magnetic moment. A charged particle which is moving in an electric field feels a magnetic field for the reasons that I told you before. If I go to the frame that moves with the electron, this is an accelerated frame, so we would have to go into general relativity. I don't want to go there. But if a particle moves with a given velocity in the presence of an electric field, it feels a magnetic field. So essentially, we have a coupling between the magnetic moment of the electron due to its spin and the magnetic moment, the magnetic field due to the orbital motion of the electron. If you want, flip this thing around, go from this Copernican view of the atom to a Ptolemaic view in which is the nucleus which orbits the electron, which is what the electron sees if we go in its own, in the frame in which the electron is at rest. And then the electron with its own magnetic moment sees the nucleus orbiting around and causing a magnetic field. So there is an interaction between the magnetic moment of the electron and the magnetic field which is due to its orbital motion. Hence, spin-orbit interaction. Let's formalize it. If I have an interaction, a magnetic moment which is in the presence of a field, it's Hamiltonian. The energy of the system is just the dot product of the magnetic moment of my particle and the magnetic field with a minus sign, meaning that actually this magnetic moment wants to be parallel with the magnetic field. Okay, now what I said is an electron, a charged particle which is moving velocity v in the presence of an electric field E, feels a magnetic field which is given by this expression. Again, this is coming from the relativistic transformation of the electromagnetic tensor field, but you can do it by saying, well, this electron is moving in a magnetic field. It feels a Lorentz force which is proportional to v cross b. If I move with the electron so the velocity goes to 0, the force has to remain the same, and therefore there must be the appearance of a field, an electric field E, which creates this force, and vice versa. So this is the relationship between the two. So what I can do is consider the magnetic moment of the electron, consider the magnetic field which is due to the orbital motion of the electron, plug it here, and I get this expression. I simply replaced B with this expression over here, okay, and replaced the velocity of the electron with its momentum, classically speaking. So the momentum is just mv, okay. Now, the electrostatic field that I have here is just the gradient of the potential, assuming that I have a Coulomb force. The field only has radial components, and it is due to the radial derivative of the potential. This 1 over r without the bold character times r is just the unit vector in the radial direction. Okay, so if I plug this into here, I get this expression. Okay, now let me skip for a moment, I'll talk about it in the next slide, several issues about factors of 2's. There are some colleagues of mine which are in the audience here, and you know that as a theorist, you might have spent a good fraction of your lives worrying about factors of 2s and 2 pi's and so on. So I'm actually chasing one right now. So factors of 2s are always a nightmare and give headaches. Anyway, let's ignore this factor 2 for a moment. Let me notice that r cross p is just the orbital angular momentum of the electron. If I express the, oh boy, now we have 11 bits on my clock. If I express the magnetic moment of the electron in classical terms, in terms of its orbit, of its angular momentum, of its rotation around its axis, if you look at Jackson's books on electrodynamics, you see that this is the usual expression that you see for the magnetic moment of a charged particle, charged sphere, which is rotating around its axis. So if I replace for r cross p the angular momentum, and for mu this expression in terms of the angular momentum, which is spin of the electron around its axis, I find this expression over here, which is an L dot product with S. So the spin angular momentum dotted with the orbital angular momentum with this coefficient in front gives me the Hamiltonian of the interaction between the spin and the orbital angular momentum of the electron. Factors of 2s. This is complicated. So first of all, this expression is correct accidentally and almost. Accidentally because we're making 2 errors of a factor 2 in the numerator and a factor 2 in the denominator that I should add. So they happen to cancel, except that one of these factor 2 is not exactly 2. It's almost 2. I don't remember to how many digits. I think the third or fourth digit is not a 0. It's 2.00 something. And that's the anomalous gyromagnetic moment of the electron. So there are 2 issues here. One, if you look at Jackson, you find this expression, as I told you, for the magnetic moment of a particle of charge q with angular momentum around its axis x. And there is a factor 2 in the denominator. The electron has spin 1/2, so I should have a quarter, but I don't. And that's because this magnetic moment for the electron is a factor of almost 2, almost exactly 2 larger than what is predicted by this classical argument. This is actually one of the triumphs of Dirac's equation. Dirac came to formulate his relativistic wave equation for the electron coming from different place, using actually Hamilton's quaternions, algebra, and so on. But he derived that expression, that equation, and the wave equation actually admits solutions which, first of all, admit spin automatically. Spin comes in for free. And 2 of the 3, but the second part is that if you go and calculate the magnetic moment of an electron, you get that it is a factor of exactly 2 bigger than what it should be. It's not exactly 2, and for that we need to go to quantum electrodynamics. We need to go to what Tomonaga, Feynman, and Schwinger did in immediate post-World War II years, and you really need to do some fancy stuff. Quantize the electromagnetic field, quantize the electron field relativistically, and then you can calculate the deviation of this anomalous gyromagnetic moment of the electron from exactly 2 in a way that is, I think, one of the best theoretical results in the history of physics. I think that calculations, which are complicated because you have to go to higher order perturbation theory terms, and to these higher orders, usually the calculations have historically anticipated the accuracy of the measurements, and every time a measurement catches up and gives you the next digit, it turns out to be in perfect agreement with the prediction of the theory. So this is a complicated story, all about a factor of almost 2. Okay, here I have it actually, 200,232, blah, blah, blah. So it's the third decimal figure, which is not a 0. The second factor 2 that cancels this error that we're making almost exactly, is that actually in this expression we miss a factor of 2, which is caused by, again, relativistic effect, or the so-called Thomas factor. So to make a long story short and simple, this is, put the equal sign, I should put a little squiggle here, it's almost exactly like this. Okay, when I plug the S here on the magnetic moment of the electron, I get almost a factor of 2 again, except for something like this third decimal place. So a very small error that we're making. So we'll ignore it for now, although of course it's very important from a conceptual point of view. Good. So what does this mean? In an atom, it means that spin up and spin down are not exactly degenerate. The spin-orbit interaction lifts this degeneracy, because if the electron orbits in this counterclockwise way in this picture, and the spin is up, there will be an interaction which has one sign in this expression over here. On the other hand, if the spin is down, clearly the magnetic moment is flipped, so the interaction is different. And this is what causes the fine structure splitting of an atom. In general, notice that this depends on the radial derivative of the potential felt by the electron in its orbital. The heavier the ion is, so the higher the atomic number, the stronger this interaction will be. So heavy elements feel a fine structure splitting, which is much bigger than lighter atoms, lighter elements. And indeed, even in solids, the spin-orbit interaction becomes stronger and stronger as you go down the periodic table. And I'll give you some numbers for the group 4 materials where the effects are really, really significant. How do you calculate this thing? Well, we have to look at, this is a perturbation Hamiltonian. In first-order perturbation theory, the correction to the energy of an atomic orbital or of a band, a dispersion in a solid, will be given by the matrix element of this expression in unperturbed state itself. So if I'm dealing with the 1s orbital in an atom, I take this matrix element, or the expectation value, if you want, of this spin orbit Hamiltonian into the 1s state, or 2s or 2p, or whatever I want to calculate. I know what is the square angular momentum in a particular state, which is given by this expression. I hope you're familiar with it. If not, I can explain and go back. I think I may do it anyway in the near future to use an algebraic way to deal with the angular momentum eigenstates and eigenvalues. So the eigenstate of an angular momentum, the angular momentum operator, are characterized by 2 quantum numbers. One tells you the magnitude of the angular momentum, the orbital angular momentum. How big is this momentum, angular momentum L of the electron, which is orbiting the nucleus. The second one is for a given z-axis. You want to know what is the orientation of the angular momentum. So you fix an arbitrary z-axis, and then you can classify the eigenstates in terms of the eigenvalues of the z component of the angular momentum. So they commute, L square and Lz commute, and so an eigenstate is characterized by 2 quantum numbers, L, which is the total angular momentum. The square of the total angular momentum is L times L plus 1 h bar square. The z component angular momentum is just h bar m. M can run between minus L and L. It can be totally up or totally down with respect to the total angular momentum, but in discrete steps. Everything is discretized in quantum mechanics. So what do? Is we consider these eigenstates and then look at the matrix elements or the expectation value of L dot S. L is the angular momentum, S is the spin. So how do we do it? We consider the total angular momentum in this picture over here, which is the sum of the orbital angular momentum and the spin angular momentum. Conventionally, it is called J. I know what J square is. It's just the dot product of the two vectors, so it's L squared plus S squared plus 2LS. L dot S is actually what I want. So I can write the expectation value of L dot S, which is what I have here, in terms of the expectation value of the square angular momenta, the total, the orbital, and the spin. And of course, I know what they are. This is JJ plus 1 times h bar squared. This is L times L plus 1. This is S. S is 1/2, right? Times S plus 1. Well, L and J depend on what is my eigenstate. For example, the important thing is what happens at the valence band, at the top of the valence band. For most of the FCC crystals, they are p states. P with the spin, with 2 spin, we have states which can have total angular momentum of 3/2, and the total angular momentum can have 4 values, plus or minus 3/2 and plus or minus 1/2. Okay, and they represent the triplet and the singlet states of spin states. So the net result is that you have an expectation value of the spin orbit Hamiltonian, or the splitting causal spin orbit Hamiltonian, is of an energy which is usually called delta SO or delta E SO for spin orbit, which has this magnitude. Notice again that there is a radial derivative of the ionic potential, so this grows very quickly with the atomic number of the material, and then there is this expression which depends on the various fundamental constants of physics, Planck's constant, electron charge, electron mass, speed of light, now depending on the units that you use, Gaussian or SI units. Okay, again, this is our expression. For example, if you look here at silicon, this is the same picture that I showed before. You see this split. This splitting is about 44, I said 43 before, well, 44, 43 for silicon. And that's, you can calculate it by knowing exactly what the expectation value of the ionic potential is. Okay, it's not a simple calculation. And you have a splitting of these bands. So 2 of the J 3/2 states go up and 1 go down. And this is the splitting that you have. By the way, this band is called the SO band. And strangely enough, SO doesn't usually stand for spin orbit, but for split off. So this is a split off band. And you see with strain how things the degeneracy is lifted even more. As I said, this term here, which is the radial derivative of the potential, grows as the atomic number of the element increases. If you look, for example, at group 4, group 4 materials, you start from carbon. Carbon has a split-off interaction at the valence band, spin orbit interaction here, which is of the order of 1 electron volt. Well, sorry, 1 milli-electron volt. So extremely small. In silicon is about 44. In germanium is about 300. You see how it grows. If you go to the next one, which is tin, is about 1 electron volt. Lead becomes an issue because it's a semi-metal. It's not a semiconductor anymore, like tin, but it's larger yet. The next one is a transuranic element. I have lots of funny stories about this transuranic element, flerovium. The longest-lived isotope of this group 4 element is something of the order of milliseconds, and yet once I got a paper to review which calculated the band structure of this object. I wonder how you verify it experimentally. You need very fast grad students who go in and measure the optical spectrum of this thing. They have milliseconds, maybe even microseconds to deal with. Anyway, so and the spin orbit interaction is actually extremely big, and that's why the interesting thing is the spin orbit interaction is so strong that actually converts what could be a semiconductor like tin into a semi-metal, because the spin orbit interaction is bigger than the gap that you would have in absence of the spin orbit interaction. And actually this has an extremely interesting consequence, which actually has been noticed by, was it 2 years ago, the Nobel Prize in Physics, 2 years ago, 3 years ago now, time flies, topological insulators, so topological properties of these materials. You actually invert the gap. The valence band goes down, the conduction band goes up, you get an inverted gap, and that is a topological insulator. So interesting properties of these materials. So that is all caused by the spin-orbit interaction. Notice that this idea that I talked here about this relativistic thing is key to all of these interesting properties that have been that are being investigated very extensively nowadays, from the Rashba effects to spin quantum Hall effects and so on. They're all caused essentially by this intrinsic magnetic field that you see when you move in an electric field, and vice versa. So this is an important issue for some materials, like some of the 3,5 materials, heavy, like indium antimonide. The valence band split here is actually bigger than the band gap. I don't remember the numbers. The band gap is about 0.16. I confuse between indium antimonide and indium arsenide. I think indium antimonide has the smallest band gap, and since antimony is heavier, actually has a bigger spin orbiting splitting, which is almost an electron volt. So it's a huge effect in some of these small band gap materials, small effective mass materials. Okay, so much so for the spin orbit interaction. Any question about this? No? So it's a relativistic effect. That's why I would like to say a few words in the near future about relativistic stuff and where relativistic wave equations are coming from. Okay. Some other considerations that consequence results, qualitative results that you can get from K-P perturbation theory is the fact that you can actually calculate the mass by using, again, not only the gap. We saw before that if you use K-P perturbation theory, you get an expression that tells you that effective mass has correction terms that have in the denominator the difference between the energy of the band you're dealing with and all of the other bands. And if you have, say, indium antimonide, in which the gap is very small, clearly the conduction band determines almost exclusively the effective mass that you have. The issue is that in some materials you may also have, if you look at a conduction band, not just the two highest energy conduction band, but you can have also the single split off bands. And then the spin orbit interaction comes into play, because the gap between this and this band depends. If you consider the conduction band, you have a gap which is increased by the spin orbit coupling. So you can express the mass as essentially the geometric average of these gaps, and it works fairly well. K.P actually in the valence band is a disaster. I mean, in general, not just K.P. The conduction bands, I think I have a plot here, are relatively simple compared to the valence band. Here I illustrate the equi-energy surfaces of the silicon valence band at an energy of 25 millielectron volts below the bottom of the top of the bands. For the heavy hole, the light hole, which is the bluish line, and the spin orbit, sorry, the red line, and the spin orbit split off bands, which is this one, 25 millivolts from the top of their respective tops. You see in various directions. This is with the axis pointing towards the page in 001 direction, and this is in the other direction. You see how complicated it is. If you want to visualize the equi-energy surface of an electron in the conduction band of gallium arsenide, it's just a sphere. It's a soccer ball, a football. If you want to visualize it in silicon, it would be an American football, a rugby ball, elongated, but relatively simple. For the valence band, it's a mess. You can visualize sort of think of a cubic pillow, soft pillow. You punch it in the middle of the faces. So it's anisotropic, it's highly non-parabolic. If you move to the other bands, they are rotated in some funny direction. So it's really messy. And you can use K.P to express what is called as warping and non-parabolicity with expression of these sorts, which are convenient to use in some transport simulation. Transport calculation in a valence band are always a nightmare because a single effective mass doesn't work. From this expression, such an expression, for example, I give you the corresponding values in atomic units here, you can extract the effective mass along various directions. You see that along this direction, the 100 is different along the 110. If you go along other directions, they're different yet. So you see how complicated things are. And finally, non-parabolicity. K dot P also allows you to consider the first order correction similar to here. What is the change on the mass and so on the dispersion that you have when you consider effects on nearby bands? And usually it comes down to what people call the non-parabolic corrections. For a two bands model, a single band can be expressed as the parabolic expression, which is this expression over here, usually called gamma. And then you have a correction. And the energy is corrected by a term. Usually this non-parabolic parameter alpha is negative, so the energy is actually depressed. You tend to flatten the bands from a parabola. A parabola will go up forever. The non-parabolic correction flatten it. This decreases the velocity and increases the density of states. So it hurts transport because you reduce the velocity, which is given by the slope, which goes down, and you increase the density of states, which in turn increases the scattering probability, the scattering rates, because you have more states into which electrons can go as final states after a collision process. Okay, any questions so far? It was a brief overview of what I assume it's already known, but we put it in a frame in which we have derived this from K dot P perturbation theory. Okay, next topic. I don't think I will have the time and the voice to deal with all of these topics today, but we'll see where we get. So, as I told you at the beginning of today's marathon class, we have calculated the excitation spectrum of a solid, so now we're happy. We have seen three methods to calculate the band structure. We have seen all the approximations that were made at the Abbatic-Born-Oppenheimer, single electron, there's later determinant Hartrott-Fock, exchange and correlation, all of these things. And how we've calculated, or we can calculate using plane waves, using tight binding, using K dot P, that's all very nice. Now we have to deal with transport. We're beginning to get there, right? That's the main subject of this class. Eventually, as far away as they may seem now, we want to deal with electronic devices, transistors. So we'll have to see how electrons move. And from what we have said so far, this looks like an impossible task. We have had so many problems already dealing with a solid, a crystal in its ground state at 0 temperature, only valence bands. Boy, what can I do now to understand how an electron moves when I add an external perturbation, an external potential, say an electrostatic potential. I will also be interested to understand how an electron behaves when I add an electromagnetic wave, so light, or any time-dependent perturbation. So it looks daunting. However, there are important theorems which simplify the problem to an extent which is, I think, surprising. And these are mainly coming from two major results. One is work that actually was done by, originally later, but in some hidden form. I think it was 1955 or 1957, I forget. The many hugely important papers that came out in 1955 from the deformation potential theorem by Bardeen and Shockley, from the high field transport in silicon by Bardeen and Shockley, from the derivation of the Boltzmann transport equation in presence of random impurities by Lattinger and Kohn. And again, the formulation of a approximated Schrödinger-like equation in a solid in the presence of shallow impurities, dopants, to know, for example, what are the ionization energies of phosphorus or boron in silicon, for example. How do I calculate that? This is an extremely important result that I will try and go to in some detail because it will be used in many situations. It leads to a huge simplification of our problems. For example, if I want to study electrons in a gallium arsenide quantum well, indium gallium arsenide, aluminum gallium arsenide, whatnot, how do I do it? Well, except for some issues about matching the wave functions at the boundaries, essentially I can use the effective mass and treat the electrons as if they were free electrons in the presence of a quantum well, so with potential discontinuities, but use the Laplacian operator to describe their kinetic energy. With the only correction with respect to free electrons is the use of a different effective mass. And this is coming from this equation. We can extend it and deal with it as we're doing now in my research group to deal with quantum transport using pseudopotentials. This bypasses or avoids some assumption approximations that we will make, like a single band approximation, for example, or weak field, but it can be extremely useful to deal with electrons which are moving in the nanostructures. The second set is a set of two theorems which go under the name of acceleration theorems that reduce our problem to F equal ma, most surprisingly, where A rather than A is the derivative of the crystal momentum, and the crystal momentum is the K vector. So it will be extremely useful, I would say crucial, in dealing with all transport phenomena that we will deal with. Examples of this stuff will be, that we will discuss, are the block or Zener block oscillations, stack ladder quantization when you have a solid in the presence of a high electric field, constant, an idealized situation, but people have looked at block oscillations. I think it was in the 80s where any conference on hot electrons in devices had at least one session on block oscillations. They were trying to make terahertz oscillators out of these things. Landau levels, which are crucial for the quantum Hall effects, for example, understanding how electrons in a two-dimensional electron gas, a silicon inversion layer, a gallium arsenide quantum well, how they behave in the presence of a magnetic field which is perpendicular to the plane of the two-dimensional electron gas. Plasma oscillations, these are interesting objects, because it will be one of the examples that we will use to quantize fields. So to go to second quantization or many-body theory or quantum field theory, whatever you want to call it, it will be one of the simplest types of elementary excitation of a solid, excitation out of its ground state at zero temperature. Shallow impurity levels, how do you calculate the ionization levels of, as I said, phosphorus in silicon, for example, which is where Luttinger and Kohn is the problem that they faced in order to derive the equation that takes their names, although it goes under many other names. Sometimes it's called the envelope or even effective mass equation, although they're kind of misnomers. And then, of course, quantization in inversion layers, quantum wells, which is what I discussed, which is again a result of the Kohn and Luttinger equations. Okay, so this envelope approximation, let me state the result. So we know that in a crystal, zero field, external field, we have our lattice potential due to the potential of the ions, we have the Hartree field due to valence electrons, we have many body effects which are represented by the exchange and correlation functionals, whatever we decide to use or we can use. And good, so we know that this is the situation, and the wave functions are our block states. A periodic component, again a remnant of the atomic orbitals for each band n, modulated by a plane wave. And in most cases, indeed, we said that we can treat this as a plane wave. Ignore the remnant of the atomic orbital. Where is it coming from? And it's coming from this. Suppose that to this neat situation that we have discussed so far, complicated but neat, it's pretty clear what we have to deal with, I add an external potential. I have a transistor, apply a potential to the drain and to the gate of my FET. So I have an external potential. And suppose that this potential is slowly varying, meaning that the variation of the potential across a single Wigner-Seitz primitive cell of my lattice is much smaller than the ionic potential. It doesn't take much if you think about it, or is much smaller than the band gap, or is much smaller than the energy scale that I'm interested in. Okay, so a smoothly varying slow potential. Conduction band discontinuities and balance band discontinuities are a different issue. We can treat them in a different way. So it's the external potential that varies smoothly. Let me consider only one band. So let me assume that this potential is also weak enough, so the electric field is small enough, so that I do not have coupling between bands. I do not have tunneling from the valence band to the conduction band, etc. This is actually not strictly necessary. It will be used to obtain the equation that is boxed in red here, but you can extend it. The equation gets different, it becomes a matrix form, but you can extend it also to account for multiple band, inter-band or intra-subband or whatever transitions. But for now, let me assume that the field is weak and I'm interested only in electrons in the bottom conduction band, okay? At the gamma point in gallium arsenide, close to the X point in silicon, close to the L point in germanium, whatever we have. Then the idea is that instead of expressing my wave function as a periodic component multiplied by a plane wave, I have it as a periodic component that close enough to a particular K point, which is the minimum of my conduction band, multiplied by an envelope, so modulated if you want, not by a plane wave, but by a slowly varying envelope, which essentially replaces the plane wave. A plane wave is what I have for an electron at zero potential. Here, this term is what I have for an electron in zero external potential, in the presence of the ionic potential, but zero external potential. If I apply a smooth, slowly varying external potential, I replace this wave function with another function, which I call the envelope, which modulates the periodic component, and this equation, this function, satisfies something that looks like very much like Schrödinger equation. So I have a kinetic energy term. I'll talk a moment about this. I have the external potential. The ionic potential is gone, has been lumped into this strange object. And this is the time-independent Schrödinger equation, if you want, if here I replace this kinetic energy with the kinetic energy of the free electron. What is this? If I take this as the K vector, this will be the dispersion of an electron, so the bands that I've calculated so far for my electrons, in which this is the lattice wave vector, the lattice momentum, okay? The crystal momentum. Formally, I replace the dependence on the dispersion on the K vector with this operator. This is a nasty operator in general. It takes about a couple of hours to show that actually the Laplace operator is a good operator, is Hermitian, is bound. If we go beyond, we have the cube of this, or God help us, fractional powers of this operator, then this operator can become non-local, unbound. It's a disaster. So let's not go into what this means in general, but formally, this is the equation that this function, this envelope function, satisfies. Okay, I get it. Let's take our time here. And I hope that you're not too tired. I mean, it's the drawback of having this marathon lectures over 3 hours. I know that I'm getting tired, and probably you're getting even more tired. So I hope you have not dozed off by now. So this is my Schrödinger equation. Okay, this is my usual lattice potential with whatever all mumbo jumbo I have to add in, Hartree exchange correlation, whatnot. Oops. Okay. Is there any question? I saw the screen pop up. No? Am I still online? Yes. Do I exist? Yes. Can you hear me? Anyone?
Yes. Yes.
Good. Okay. All right. So I know we're getting tired, all of us, huh?
Thank you, Professor.
All right. So this is the equation that I want to solve. Again, this is my external potential that I apply by hand by turning a knob on my power supply on my device, and is smoothly varying. So what I do is I assume that this my unknown can be expressed, well, this is not an assumption, my unknown can always be expressed as a linear combination of the block functions. And that's because the block functions are a complete set of basis functions in my Hilbert space for my single particle Hilbert space with some coefficients, whatever these coefficients are. So I can write it expanded this way. I'm using for now finite volume normalization. So this volume over here is the usual nuisance that I have to carry around whenever I deal with block wave functions. Good. So the usual thing, I plug it back in, the Schrödinger equation, this expression, and I find this. This is because this term over here applied to each of these basis functions gives me just E, right? It's the eigenvalue problem that I've already solved. This is my band structure. These are the coefficients, okay? And then I have this term. And this is the troublesome term. The usual thing, let me project this equation into the bra of these wave functions, right? The usual thing. So I take the bracket, and so I have to look at each term individually. So notice that I have terms which will have the sum over n of k of these coefficients times psi multiplied by psi star on the left-hand side. I can use actually the expression that I have over here for the block functions and writing it in this way. This is just plugging the block expression for the psi mk prime and psi nk. Okay, and these are these fixed coefficients that I have in front. So this becomes an integral of essentially these the plane waves, the k that I have minus the k prime because I'm taking the complex conjugate, the gm minus g prime again because I'm taking the complex conjugate. Now notice that this integral is a delta function, okay, because it's just an integral of the plane waves. So let me now restrict my attention to the case in which k and k prime are within the Brillouin zone, which we can always do by adding a sufficient numbers of g vectors to these vectors. So these conditions can be met only when k and k prime are the same and g prime are the same. And g, it's only discrete values. These are a continuum of values, so they have to be zero separately. So the net effect is that actually this becomes a delta, a Kronecker delta. And this complicated mess becomes simply this coefficient here, okay? Now the real problem is a different one. So this takes care of this term, sorry, where am I? This term and this term. We get deltas, delta of n and m. The more complicated story is what happens to this potential. And that's where the problems are, and that's why you have to assume that this potential has some properties, such as being smooth, being slowly varying over a unit cell. So my equation now becomes a linear system of equations, for these coefficients, the expansion coefficients. Notice that this is like a matrix, where this is the diagonal, these are the off-diagonal terms, and this is my eigenvalue problem, right? So I have to find what the E's are for this coefficient, or if he is fixed, what is the solution of this linear system. So I have to find how to write this in some simpler way. This I can write it this way, right? It's just the matrix element of the external potential between two block functions in band n and vector k prime, in band m and vector k. Let's write the external potential in its Fourier components. Again, notice now that Q is a general Q. This external potential is not periodic anymore. Doesn't have the periodicity of lattice. So this is really a genuine Fourier expansion. Written here as Fourier series simply because I'm using a finite volume normalization, but in general, this is a Fourier expansion. So I plug this into this equation, this expression here, and then I pick up the various g's that I have that are left inside the cores, the periodic component of the block function, and then I have this term. Notice that if these were absent, so if I were dealing with electrons in free space in the presence of an external potential, this would be 1. This would be just the delta function that expresses momentum conservation. An electron scatters with a potential which has a Q component VQ, which I pick over here, and then its wave vector, K, becomes K plus Q, or minus Q, depending on how you pick it. So it's just crystal momentum conservation. If I'm not in a crystal, it's momentum conservation. Here it's more complicated because I have this nuisance of these orbitals, if you wish, the periodic component of the block wave function. So let's do the usual trick. I have a integral of the entire volume. Let's split it into a sum of integral over cells. And that's because these wave functions are localized in each cell, as we saw already, I think last week. So we can ignore the integral of these objects away for their single cell. So we have now split the sum over the entire volume into the integral of the entire volume into a sum over integrals over single cells. And here, the coordinate r, I've extracted the coordinate of each cell site, and this row will be just defined by these expressions. So I've just changed variables. The usual thing, this term is a Kronecker delta, can be non-zero only when this is a vector of the reciprocal lattice, some G double prime, whatever it is, okay? And then what I've left here is whenever this is true, this is 1, and I get the number of cells, which cancels the volume that I have here, the number of cells that I have in this volume. And this is what I've written explicitly here. So the integral over the volume, so the normalization volume, which is n times omega, where omega is the volume of a cell, the sum over these objects has become just n, which cancels the n that I have here. I'm left with an integral over the volume of a cell of these objects, which is sort of an overlap integrals between two block states in different bands. And then I have the Fourier components of my external potential at the difference between the two k vectors of the two wave functions. And then, of course, I have this nuisance of the fact that I have to sum over all possible G double primes, because this is 1 in each cell for each G double prime. Okay, which I can rewrite like this, noticing simply that the dependence on the G's of these wave functions, of this wave function, the periodic component of the wave function, is just an exponential. So it can be written as something which, if I didn't have a crystal, then the sum of the G's would disappear. This would be just 1. It would be just a Fourier component of the external potential. No big surprise, is what we said before. And now we have to sum over these umklapp terms, which involve the overlap integrals between the two wave functions. That's where the simplifications are needed. This is general, and actually I can use this to solve my Schrödinger equation. So to put it in another way, I've accomplished nothing. So far, I have only rewritten the Schrödinger equation in a different way, but this is exact. No approximations made so far. And that's why we drag along many bands and we have all of these G vectors and so on. Now, let me make use of the fact that I anticipated that this potential very slowly. Very slowly means that exactly the same thing that we saw for the empirical pseudopotential while we introduce, pseudopotential, while we introduce pseudopotentials. Slowly varying means that the short wavelength components, so the large Q component, of this potential, oh boy, I'm sorry, I lost my page here, okay. They vanish very quickly as Q grows larger, because of the smoothness of the potential. So above, so we can actually ignore the terms G double prime. Remember the G vector is a very large vector compared to the K vector that an electron can have. A G vector is in units of 2 pi divided by the lattice constant. So it corresponds to a wavelength which is essentially the size of a primitive cell. An electron near the bottom of the conduction band has a very long wavelength. So these K vectors are very small. So essentially what we do is forget the sum of the G. And in here also, we'll assume that it's G double prime is equal 0. So I have just the V external of K prime minus K. Let's assume also that this V external is smooth enough so that the K that enter here in this overlap integral do not change too much. So the K prime is not too different from K. Again, these are wave functions which are the remnants of the atomic orbitals. So they oscillate very fast inside an ion core, actually. Okay, if they are pseudized inside the cell, because we have eliminated that, but still, when K changes not too far away from the bottom of the conduction band, it spans a small region of the Brillouin zone. So the dependence of K that varies over the entire Brillouin zone can be ignored. We can assume that these two guys are the same K, that the dependence on K prime here is very weak. And so we can assume that they have the same K. In this case, you know what happens. At the same K, these are eigenvectors corresponding to two different eigenvalues of the Hamiltonian where n and m are different. So they will give you a delta, Kronecker delta of n and m. It will give you 1 integrated over the cell when n is equal to m, 0 otherwise, which is what I've written here. Okay, so now we see what we have. We are reduced to a very simple case. The complicated form, I remind you how complicated it was. It was this nightmare here. Okay, now we have reduced it to the fact that it is just the Fourier component of K minus K prime. This matters. The difference between K minus K prime matters because this V varies very smoothly. Instead, we've ignored it into this integral where this functions very, very fast. And we get just a delta, which tells me that can stick to one band only. Again, the fact is that I've said I don't move too much away from K prime, right? If the field is very large, so if V external is large, I cannot do that anymore. Okay, now I have interband transitions. But again, I could retain it. The price that I pay is that now I would get a matrix equation rather than a simple scalar equation. So my Schrödinger equation has become this matrix equation for this coefficient C. But now let's go back a minute. Let's define an envelope wave function. You remember what we were started from? Started from the fact that we said I can replace this with this envelope here. Let me define an envelope. Where am I? Here, which is just the essentially a Fourier components expressing its Fourier representations as plane waves with amplitude which are given by these coefficients, which are the solution of this matrix equation. So now let me go back and look at what my wave function was originally. Remember, this is where it started from. I assume that the wave function of the problem that I want to solve is a linear combination, linear superposition of black waves with some coefficients. But this, we said, well, I can ignore the dependence on G of these things or K on this thing and just replace it with a K equals 0 over here. And this is, if I extract this piece over here, this does not depend on K anymore. So I have just this, which is phi, with a volume, normalization volume in front, which is just the envelope times the periodic component calculated at K equals 0, which is essentially what I wanted to have. So we're back to what we said, and that's our final result. So we can express, let me go back again here to the beginning. We can replace, we can express the solution of my Schrödinger equation in the presence of an external potential by a wave function, which is essentially the block wave function at the K point at the bottom of the conduction band, but instead of having a plane wave modulating it, I now have this envelope which satisfies this equation. Why is it handy? Is it handy because if now I take this nasty, in general, non-local operator and consider parabolic bands with an effective mass m star, this operator becomes just the kinetic energy, except that instead of the free electron mass, I have the effective mass of the material. And so this is now looks very much like the conventional Schrödinger equation for electrons in, not in a crystal, but free electrons, with the exception of the mass, which has been renormalized by the presence of the lattice, in the presence of this smoothly varying potential. And this is what is being used to study, for example, the wave function of electrons in inversion layers, in quantum wells, and so on. This equation goes under very many names. I don't know what one you prefer. Again, Slater was the first guy who sort of proposed it. Luttinger and Kohn are those who derived it in the presence of, to study the problem of, as I said, the ionization energy of shallow impurities. Because we're dealing with the envelope, sometimes it's called the envelope approximation, and because it's mostly used when we use a parabolic dispersion with an effective mass, sometimes it's called effective mass equation, effective mass envelope equation, whatever. However, I'd like to call it Luttinger-Kohn or Kohn-Luttinger because it's more general, particularly if we don't make this assumption anymore. It really, it becomes exact, almost exact. And then we can treat more generally problems which involve interband tunneling. We can use dispersions which are more complicated than the simple parabolic dispersion by retaining the pseudo-potentials, for example, or the tight binding hopping parameters in this that becomes replaced by a matrix of rank equals to the number of bands that we're considering. So it's more general, and this is just a particular case. Okay, I talked about effective mass. Since I'm really running out of voice here, and my throat is beginning to hurt, I'll just tell you what another definition, which is the obvious one, of the effective mass and how it relates to this expression. So where do we get from here to here? Well, if we have an arbitrary dispersion, again, I remind you that it's called dispersion from the fact that electromagnetic waves in a medium in which the index of refraction depends on the wavelength leads to packets that disperse, that spread as you go around, because the velocity of light depends on frequency or wavelength. So if I have a dispersion calculated no matter what, no matter how, with tight binding, with DFT, with GW, with whatever you want, I get some dispersion for a given band. I can always expand it around the minimum or an extreme point, the minimum of the conduction band or the top of the valence band. So this is the first term that I get from my Taylor expansion. The first term, the first derivative is 0 because I'm assuming that I'm expanding it around an extreme point where the first derivative, so the gradient, is 0. So there's no first order term. There is a second order term, of course, which involves, this is a compact notation to represent the this object, the second derivative with respect to ki and kj multiplied by k minus k0I and k minus k0j, and there is the 1/2 which comes from the second order of the second term of the Taylor expansion. Now I can assume that this is essentially an expression which is similar to what I have for parabolic bands, measured from this extreme point, and express it in this form. So by replacing k minus k0 with the momentum operator, that I would have a momentum operator, there's no h bar because this is a wave vector, I can write it in this form. And then I can define the effective mass essentially as the term that I need to express this correction term, which is coming from my expansion, so my band structure calculation, as a homogeneous term in the square of the displacement of the wave vector around the minimum, around the k0. And so the effective mass is essentially defined as a matrix or a tensor, if you wish. Actually, the inverse is defined this way, such that I can write my dispersion as a parabolic term. It may not be isotropic, may have a different curvature depending on which direction I have, but it's parabolic. And so that's what defines the effective mass tensor, okay? And so I can write my wave equation, this object over here, can be written more generally in this form, having simply replaced my dispersion with the operator, so this complicated operator in this form. And so my differential equation becomes simply a wave equation, which is anisotropic. I have an anisotropic mass. The typical case that one considers and one has to encounter is for 3-5 compound semiconductors in the conduction band. This is actually isotropic. This mass tensor actually has 3 diagonal elements which are all equal. For silicon and germanium is a little more complicated. Usually you have one mass, it's a diagonal term, but 2 of the terms are equal and one is different, the longitudinal versus the transverse mass. So these are the typical situations that we will encounter. And next week we'll go into the acceleration theorem and single electron dynamics to see how we can apply all this machinery that we built so far to deal with problems in which we have a crystal in which we add an external potential. Okay, I'm really running out of voice here. So are there any questions? Have I gone too fast, too slow? Are you happy? As happy as you can be. All right, if not, so I have uploaded the homework assignment. You don't have to turn them in. Please. I heard something, but I couldn't understand. Can you repeat it?
I think later.
All right. Okay, so if there are no other questions or anything, I will update the slides because I keep changing them. Again, do try and do the problem set that I assigned before looking at the solutions. So don't cheat yourself. And if you have any questions about the class, about the problems that I've assigned, just let me know and I'll be happy to reply by email or whatever means you wish. Okay, so have a good weekend. I spoiled your Friday night and I'm afraid that's going to be the norm. And I'll see you next Friday morning then, afternoon. Okay, have a good weekend. Bye-bye.
Bye-bye, Max.
Thank you, Professor.
Thank you, Prof. Bye.
Bye.
Ciao Massimo.